What I'm saying is that you can do some scattering experiment and then produce a region in this false light. Doesn't have to be a thermal. Doesn't have to have a temperature. But what the important thing
you have in mind some bubble that expands or shrinks, and what is the physical picture that you like?
But there will be a bubble in this region, but that bubble will decay back into the true vacuum in quantum physics. Without gravity, you produce the bubble, but that bubble is metastable, it will decay back. So in fact, it's not that interesting. In a sense, we can probe this false vacuum inside lab. We can produce a region of this false vacuum and study, and eventually it will go away. So now big gravity.
Yes. Yes. Okay.
This becomes non-trivial because it is actually classically forbidden. So let me say something else here. If you think about the Penrose diagram for this process, although we normally draw Penrose diagram for gravitational things, but we can do it here too. So this is just the Penrose diagram with Minkowski. And what happens is that we are basically thinking about doing some experiments, sending in some fluctuations from the past. And then eventually, whatever happens, we will get the asymptotic space of the future. So the asymptotic structure of the space-time remains the same. We always in Minkowski, because we did not turn on gravity. Now, what happens if we do turn on gravity? Then, of course, we should change. If we turn on gravity and we make a big bubble here, then we are changing the asymptotic structure of the space-time. Are we now occupying Andre's class?
No, we won't go downstairs.
Okay. No, the organization of this is as complicated as the mechanism that I'm going to propose for Uptunneling. It's extremely complicated. Okay, so then we are if we turn on gravity, then we are going to change the asymptotic structure of the space-time, and that is going to be forbidden classically. So why is it forbidden to produce an inflating bubble? Because having an inflating bubble, it means that we will have something which is called an anti-trap surface. So what is anti-trap surface? What is a normal surface? So the normal surface, say, for instance, the surface of the ball or the surface of this bottle is a normal surface in the sense that if you consider a light cone of this surface, it will have two components. So now I'm reducing to one less dimension. And now this is a space-time diagram. So if I think about the light cone of some surface, so think of this circle as being my surface, reduced one dimension. Then there will be a component of the light cone which is shrinking and a component of the light cone that is expanding. So these are called normal surfaces. If we are inflating space-time and we consider a very big surface, a surface whose size, or the sphere whose size is larger than the curvature length of space-time, then what is going to happen is that both light cones, both sides of the light cone of this surface are going to be expanded. That is called an anti-trap surface. And then if you have anti-trap surfaces and we satisfy non-energy condition, then was another assumption that I won't say unless someone asks, then Penrose proves that we are going to have a singularity in the past. There will be an initial singularity. So now let us go back to our setup. Our setup was that we want to start from an initial condition, which is sending some stuff from asymptotically Minkowski universe. So there was no initial singularity. But we want to produce an inflating bubble, which according to Penrose will imply an initial singularity. This is something that you might have heard about in the context of inflation. Usually it is said that inflation is past incomplete. It cannot be eternal to the past. There has to be an initial singularity. So therefore, this process will not be a log classical. And therefore, one should ask the following question. Is it possible to tunnel from this true vacuum to the false vacuum quantum mechanics? And this is a question that was asked about 30 years ago by Fahey, Goose, and Guben. And the title of their paper was, is it possible to create a universe in the lab via quantum tunnel? So they were aware of this obstruction, classical obstruction, and they were asking exactly this question. Now, of course, this procedure is production of the universe in the lab, because even if you imagine now we are living in the seated space-time, inflating space-time, we want to think about creating, and imagine we have some other false vacuum. You can ask whether we can create a universe in this false vacuum in the time and scales of laboratory rather than the time and scales of or inflating universe. Yeah.
So this anti-trap surface, in pure de Sitter, there's no singularity in that pass-or feature.
This has to do with that other condition that I didn't say.
So some of the statements, if you add a little bit of anything else besides vacuum energy and it's expanding, then pass there's a singularity, it's contracting.
Right. So in de Sitter, as you know, there is no singularity in global de Sitter because it is closed. And Penrose singularity theorem applies when your Cauchy slices have a universal cover which is infinite. So in this case, the Cauchy singularity theorem does not apply. But I would consider global de Sitter very fine-tuned the space-time, meaning that I wouldn't call it a solution to the initial singularity problem of inflation, exactly because of what you said, because its initial condition would be, if I perturb its initial condition of global de Sitter, probably I will get infinite back reaction at the neck of de Sitter.
But how do you know you can't create? I forgot how this proof works. I mean, why can't you create a universe in the lab that has compact Cauchy slices or something like that?
Oh, well, here it is guaranteed because I want to be asymptotic. I mean, because here I know that my Cauchy slices are non-compact. Okay, so yeah, this question was asked by Fahey. They can do it quantum mechanics. And yeah, maybe I should say a few words about.
Just to understand what, so really you are aiming to create anti-trap surface. That's the definition of inflating power, right?
Yes. Right, so what is the motivation for asking the question? First of all, just curiosity, because it's a process that is classically forbidden. Now you talk to different people, there's a range of opinions. Some people say that quantum mechanical, everything is possible, so this should also be possible. Why not? And others will say that no, this is some, for some reason, the Sitter is mysterious and we shouldn't be able to produce. So it's not totally obvious that this process is allowed. So it's just it's just a matter. One motivation is just a matter of curiosity. Is it really possible to create this inflating bubble or not? The other motivation is perhaps to think about the issue that I mentioned about inflation. Inflation, as I said, is past incomplete, and you could imagine this as a mechanism, as a mechanism for discussing the initial condition for inflation, as a scenario that led to inflation at the initial times of our unit. The initial, basically as a theory for the initial condition of our universe. Right, and what about these earlier works? The earlier works, they proposed one such mechanism for this uptunneling. So this is this paper of 30 years ago or so. However, this scenario that they proposed basically corresponds to some Euclidean instanton, and that Euclidean instanton that they proposed for this process has some singularity. So it's not there is no consensus whether this is a valid solution or not. Therefore, it seems that it would be nice to have an alternative solution that doesn't suffer from that singularity, to at least know whether this is a possibility or not. So I'm not going to talk about the Fahey-Bouscoven instanton. I'd be happy to discuss it later after talk, but I'm sure that already I won't be able to actually explain what is the scenario that I am proposing by the end of the hour. Okay, so yeah, let us move on to explain what I'm going to. So some background. So we want to talk about the possibility of a tunneling process, something that is not perturbatively is not alone in quantum gravity. So how do we discuss this? Is basically the approach that we can follow here. The best thing that we can do in such situations is do semi-classical gravity. And
sorry. Does it follow from what you already said that it's not allowed perturbatively? Because so far I just said it's classically not possible, right?
So far I just said classical. Is it obvious that I cannot do it perturbatively? Well, I would say that's just the general situation, general fact about barrier crossing. So that I would say even in QFT I wouldn't.
Well, but you said initially if you have enough energy, you can just classically go over the barrier within QFT.
That's why classical it is forbidden.
Right.
That's a classical forbidden. Perturbative I would say even in QFT is forbidden.
No, but why do you want to do tunneling? Because in QFT I can do it classically.
Okay.
Which doesn't involve any tunneling, right?
Right.
So
on the other hand,
so basically,
in
if I start
gravity,
classically,
so I would say classical is forbidden in gravity and perturbative is forbidden in QFT. Okay, I don't know. Maybe it's possible. I don't think I have a theorem that is impossible. Perturbative about quantum mechanics. Yeah, I don't know. But I seriously doubt it because in QFT already we cannot perturbatively go up. So I don't know why it should become suddenly possible.
no, but you can start classically and then, well, roughly speaking, because maybe the analogy condition can be violated at the perturbative quantum corrections that will help. I don't think that's the case, but at least one can think something like that may happen. That quantum perturbative violation of analogy condition would be enough to circumvent
the old precision solution. If you give enough energy, it will never stop there. It's false. Like if you say that this is just a classical mechanics problem. If you kick a ball, it's enough energy. It will overcome this hill,
Yeah.
but it will never stop at this.
Yeah, but I don't want to stop that. I need to get there.
I think I don't want to stop.
No, I don't want to stop. I want to get there and inflate, right?
Yeah, I mean, I guess with 1 degree of freedom, yes, but here there are more degrees of freedom. So in principle, you can imagine some region is trapped there while the rest coming back. But okay, I seriously doubt it is possible perturbatively, but I don't have a proof. So anyway, I want to try doing it semi-classical, and let me just give a little bit of introduction. So what is the idea of this approach? So it's good to talk about Schwinger. Schwinger as a bar model. So imagine I want to imagine someone says that we have magnetic monopoles, and we want to talk about the probability of production of magnetic monopoles inside the magnetic field. So for magnetic monopoles, I don't have a field theory description. How can and they are heavy objects. So what is the way to estimate the probability for production of pairs in the magnetic field? This is a standard procedure using Euclidean path integral. And so the basic idea is that the Euclidean path integral can be thought of as a way of producing a wave function, vacuum wave function. So this is just in quantum mechanics. If I want to find the vacuum wave function, I can do the Euclidean path integral with the boundary condition given by the argument of my wave function. This. And okay, so now, this is the general idea. In fact, it's the idea that we typically use it when we do even normal perturbative field theory computation. Now, this general idea, now we want to apply it to field theory. Say I have a magnetic field B, and I want to talk about the production of monopole, anti-monopole. So what is the Euclidean process that would correspond to the pair production of this monopole, anti-monopole? It is a process in which I just consider point particle, charged point particle moves in the magnetic field, but in the Euclidean version of that. And then at a particular point in time, I will do a bit rotation of that to Lorentzian time. So there is a magnetic field E. Here is Euclidean. Here is Lorentzian. I consider a classical solution of a charged particle moving in this magnetic field. And then at the particular moment, which is called the moment of time symmetry, I rotate this, weak rotate this into Lorentzian, and that would describe the production of a pair of monopole, anti-monopole. And then I can evaluate the action for this process, the Euclidean action, and subtract from it the action that I had in the process in which I did not produce this particle. So I will compute delta SE, the change in the Euclidean action. This is a trajectory with a typical size r. And this r is related to the acceleration of the particle in the magnetic field. So this is supposed to be a circle with radius r over the m divided by q times p. So if I compute the action,
Is there a reason you talk about monopoles and not electrons produced by electric fields?
Yeah, because I didn't want the perturbative description for the exist. No, nothing beyond that. No, there is another reason, because then I want to talk about magnetically charged black holes. Again, because I don't want them to discharge fast. So what is the difference between the Euclidean action of this process and the process in which I don't produce any particle? That would be of order of the mass of this monopole times the size of this orbit, which is of order m squared over qp. And then the probability for the production of this would be estimated as long as this action is big. The difference in the Euclidean action is big, would be of order of e to the minus twice delta s, which gives actually the right exponential, the right exponent for the production of particles. So in the case, if you apply it, for instance, to charge to electrons, you have other methods for computing, and this will agree with those other methods of computing the production. So what is the moral lesson here is that if I can do Euclidean computation to get the, first of all, show that a process is possible, a process that would not be allowed classically or perturbatively is possible quantum mechanically, and it can give me an estimate of the rate of this process if I can compute the action. So we want to do a similar thing for that process, come up with some kind of Euclidean process that ends this expanding the Sitter bubble.
This is very similar to the result that you get for ordinary Schrödinger when you create a quark-anti-quark pair. Then the probability would be also e to the minus m squared over the electric q times the electric field. So
Right.
it's very similar.
Right. All right. So now we want to turn on gravity. So imagine we turn on gravity, and now you can think of this. Imagine if you have gravity, this monopole, anti-monopole, this charged particle could actually be a charged black hole. And this pair of, then we go to the Lorentzian picture, this pair of charged particles that we have would be two charged black holes which are connected in the interior. So now we want to talk about Reisman-Nostroff black hole. So these are charged black holes. Metric is this one. I'm using some units. I don't specify. And I also draw most of the numerical factors, but
It's a square.
oh, sorry, yes, that I shouldn't have. So this metric has two horizons, inner and outer horizon, given by this formula. There will be there's an extremal black hole when Q is equal to the mass, and the Penrose diagram for this diagram is it looks like this. So this is the Penrose diagram for the extended geometry. So of course, this solution could be just describing a charged star outside of it, like the same way that Schwarz's solution would describe the spherical symmetric mass distribution outside that. However, if we look at the vacuum solution, if we maximally extend it, then there will be the geometry will have other asymptotic regions. So we go inside the horizon and we can extend it beyond. So there will be two asymptotic structures and even actually infinitely many. But I don't care about the rest. Now imagine we can think of identifying the two sides of this this asymptotic region. Then this will be describing two approximate. It will be describing two charged black holes with opposite charges, which are connected from interior, but also they live in the same asymptotic space. So here you can think of these two charged black holes that are produced in the magnetic field as being the two sides of this connected geometry.
Is there some kind of wormhole?
Yes, exactly. It is a wormhole. So if I look at the spatial section of this geometry, the spatial section of this geometry will look like this. Again, I'm sorry. So here in this diagram, every point corresponds to the sphere because we are in 4 dimensions. Here, when I'm drawing this, so this is, I'm basically should think of these 2 points as being a sphere, so two dimensions, two spatial dimensions have been reduced. This is like the radius.
So it's somehow violated null energy condition.
No, it's
Because
not.
the wormholes usually violate null energy conditions.
But actually, this is not a transversal wormhole. It's not traversable, right? So it's because this is the Penrose diagram, right? So you can never send a signal that goes to the others. It's similar to the wormhole that you have in Schwarz, extended Schwarzschild geometry. Yes, so non-energy condition, but in these regions, non-energy condition is, in fact, no, sorry, it's not vacuum, but non-energy condition is not violent.
So why is it wormhole? Why is it just two separate magnetic black holes? Which have the opposite planes, they just exist. No.
Why is it not that
Well, just imagine there is just two magnetic black holes with opposite charge. So why do they share? Why do they have this structure? Why
I'm
don't
just
they
saying
have-
that this is a possibility. This is a solution of that. This is a classical solution of this path integral that I'm doing. Therefore, this process is possible. In fact, this metric exists.
No, how it is.
Right. It was studied by Straminger and Garfinkel. I'm amazed that it exists, but it I don't attempt to write the proof. Oh, okay. If you wanted one-sided black hole, you needed more structure because one-sided black. If you have one-sided black or two one-sided black holes, you have to somehow end the geometry inside them, which means that you need to have some stuff like charge, maybe monopoles to end it. I mean, I'm saying the usual thing. If you want a one-sided black hole, there should be some matter to end the geometry. Otherwise, you wouldn't get a one-sided solution, just a pure geometry.
Like, probability is non-zero, but it takes zero volume in phase space. So you can create it, but it takes like 1 point.
No, I'm not claiming that this process that I'm proposing is a likely process. The question is that there is a question that we want to understand if its answer is impossible or possible. It might be extremely unlikely. In fact, everything that I'm saying here is very complicated. So it's probably extremely unlikely, or in most QFT in most models or most situations, maybe it doesn't happen. The question is whether it is a possibility or not, whether it's forbidden or not forbidden. because of some weird quantum gravity reason, not because, for instance, I don't have the right ingredients in my model.
It might not be relevant to what you're saying, but that inner horizon made that stable. Right? So,
Yes, yes. This one.
Yeah, that,
Exactly. So this is normally it's the expectation is the general expectation is that this inner horizon is a Cauchy horizon, and that is there only in fine-tuned situation when we have a lot of symmetry. But if we perturb it, perhaps because this is a point of infinite blue shift. So if we perturb geometry, perhaps we get an actual curvature singularity. So yeah, I don't care about the extension of this. In fact, I really think of it as just a two-sided black hole. All right. So there is now. Why am I talking about this? So far, we have talked about producing this wormhole from two charged black holes on the two sides. Now, the final goal that I'm gonna pursue is that to produce this bubble of the sitter in the interior of this wormhole. Somehow, I want to argue that here is a more controlled environment for doing this surgery and putting the sitter bubble, doing this
harder because
uptunneling.
of asymptotically near the horizon, the rest of nothing looks like anti-de-Sitter.
Exactly, because
So
of that.
much more harder.
Right, yes, so it's just because of that, because the computations become much easier in this setup. But okay, so let me talk about this Georgetown Geology. When did I start? So I have about like what 15, 20 minutes.
Thank you.
Okay, so let me talk about Georgetown geometry, which is essentially metric can be written like that, except that here if STS is 1 minus h squared r squared minus over r, different. And how does the Penrose diagram look like here? The Penrose diagram looks like this. The topology is the topology of S2 times spatial topology is the topology of R times S2 or interval times S2. So one can decide what to do with this interval. Perhaps one thing that one can do is to identify the two sides here. Now again, here there will be two horizons, the cosmological horizon and the black hole horizon. And again, there's our plus and our minus, and then and let me also say that in general, then if we look at the spatial topology, so this is something that I said in Word. Spatial topology is now here after identification will be S1 times S2. Here will be S1 times S2. And then there is more complicated, I'll say that. Or if I reduce one dimension, then it looks like its own. So the idea is to cut a piece of this and implant it inside this wormhole. So now if we do that, basically the geometry that we are going to get, if we just focus in this region, is on the inside the wormhole of this geometry. So here then we are basically inside. If this bubble didn't exist, we were inside the black hole, but this bubble will nucleate inside. And then we have this domain box. We have columns. So there is these are the domain box.
But how do you see? Because of if you it's very well known that near from a place black holes near the horizon you have anti-de Sitter space,
Yes,
and you want to connect anti-de Sitter space to de Sitter space.
yes. Oh, okay.
How do you translate from it?
That's exactly what I'm gonna do. But yeah, exactly. So yeah, let me just so finish this. So this thing you should think of it as being just the interior of this wormhole. These asymptotic regions will connect here. Okay, and then the blue things will connect to the asymptotic Minkowski space. Right, so
What's the matter?
what's the metric? Okay, I got it. So the metric, right, so now I want to, as you mentioned, we are going to consider the regime in which we are going near extremality. Near extremality, what happens? The simplification that we have is that this throat region becomes very long, and we have an approximate ADS2 plus S2 description inside this region. Similarly here, when R plus and R minus are near each other, then we have an approximate description, which is DS2 process. One thing that happens is that even though there is this approximate description DS2 cross S2, I should emphasize that as we go near the future horizon here, the S2 will expand, and eventually this region will be a normal four-dimensional inflating universe. So as we go to earlier times here, it is anisotropic because in one direction it is expanding very fast. In the other direction, the size of S2 is relatively constant. But as we go toward future, this will approach the normal. Locally, it will look like normal DS4. So basically, producing this region will achieve the goal that I had. This will produce a normal inflating unit inside this wormhole. Now, what is the advantage of going to this near extremal approximation? Exactly the fact that we have this approximate description when we can reduce dimensionally reduce to a two-dimensional setup where we have 2D G mu nu and a dilator. So now what are the metrics? So now on the we have the let me also mention two other things before actually writing the equation. In addition to considering being near extreme, remember I went a little bit too fast. So we want to make some other simplifications in addition to going to the near extremal region. These are actually simplifications that was also made by originally by Fahey Goose and Google. This, these are two, so let me. So one simplification is to assume all three symmetry. Why is this useful? When we have all three symmetry, then by Birkhoff's theorem, the geometries on the two sides will be fixed. Therefore, what will be important is basically just this interpolating region between two geometries. And then the other simplification is the thin ball approximation, which means that instead of talking about a field profile that takes me from the true vacuum to the false vacuum, I'm just talking about the domain ball with an appropriate tension and charge that interpolates between these two geometries. So this will be valid if the thickness of this region when the field is interpolating is small compared to the curvature. These two approximations or simplifications, basically this problem reduces to finding the motion of a domain ball between these various geometries that we are talking about. Okay, and then the third approximation, the simplification would come from going near extremality, because if we do that, then we will be basically talking about a two-dimensional problem where we are gluing 2D geometries or 2D dilatant gravity solutions across some particles, because the domain was after this reduction to 2 dimension becomes this particle. Okay, so now what are the two geometries? On the one side, it is ADS2 times S2. But the size of S2 is constant, so RS squared we take to be the extremality radius is greater than 1 plus phi, where phi is much smaller than 1. This plays the role of the dilaton. And then the metric is, now I mainly care about Euclidean solution because here is basically the setup that we are working in. We want to find Euclidean solutions that after rotation to Lorentzian will end up with this configuration. So here the Euclidean metric would look like the rho square, rho times the phi square. It will description of TR part of this metric, which after going to Euclidean, it basically is the geometry of a disk. Actually, I should draw it. It's loose.
This is O3 of the three space coordinates. So what is this O3?
It's just a spherical symmetry.
But you know, there was this solution of Coleman, which was assuming Euclidean O4.
Right, so that was more symmetric than this.
Well, but it turned out to be a wrong solution. So this assumption that there is such a, so the assumption that the symmetric is this solution was found out later to be wrong. We will follow this papers of Coleman exactly about this two asymmetric potentials.
Okay. Yeah, well, I should just say that Coleman was mostly interested in down tunnel. But here we are considering uptunneling. So Coleman does not have
he didn't consider that.
You're right. But yeah, here is I'm assuming less symmetry than Coleman. This is just a spherical symmetry.
Right.
In the case of Coleman, the O4 is broken, not perturbative. How is it? Not perturbative.
Half conflict that discover that's a permanent mistake.
Okay, so this Euclidean geometry is just this. And this, there is a point, there is horizon here. This blue line should correspond to this. Of course, ADS geometry has a boundary. We are not going all the way to the boundary of ADS. At some point, it has to match to the asymptotic solution, which is not ADS. So it is just approximately ADS. So this blue line would be some UV cutoff that corresponds to that. And then on the de Sitter side, we will have the DS2 Euclidean DS2 solution will be just a sphere. Well, I don't draw the sphere, but the question is how do we glue these solutions together? And there are some ingredients that enter this gluing. These ingredients are essentially I need some domain balls that interpolate between the theta between these two geometries. But in addition to those domain balls, there are, in my construction, there are also some branes, massless. Sorry, not massless. Neutral and charged branes. So for now, let us just consider this solution, ADS2, which after rotation to Lorentzian will look like just ADS black hole. Now let us imagine that I have some perturbations. The brain with the finite tension in the interior here. Then there is a solution here that looks like this. So here I'm just putting a brain with the tension sigma naught. Then the geometry that we will have will be similar to that, except that the throat of black hole will be extended, will be long. Okay, so now, oh, by the way, so how do we just find this solution? This solution that I'm just drawing pictures, but actually these are essentially the solving the Einstein equations in the presence of these domain balls, which are spherical asymmetry. Basically, it reduces to doing some solving some junction condition for this phi solution. So here we have some metric that I wrote here, and then there will be a phi solution which looks like, for instance, here is A times cosine hyperbolic of rho, and then the equation that is satisfied that determines the motion of this domain ball is basically a particular. It's just the statement that phi has to be continuous on the two sides of this domain ball, and this derivative has to have an appropriate jump. So if I call the normal xc, then I will have xc mu times d mu phi, r minus def, right minus def has to be sigma, the tension of the brain. So this solution, these two conditions uniquely fix the trajectory of this domain. Now, the extra thing that I need for this Uptunneling set of solution is that there has to be a coupling between these branes. So this neutral brane should be able to decay into the domain balls that separate the Sitter region from the ADS region. That means that if I have sigma naught as the as the tension of the neutral brane and sigma as the tension of the charged brane that separates the two solutions, then here there will be an angle theta, and twice sigma times cosine theta has to be sigma naught, which tells me that sigma naught, there should be a kinematic condition that is satisfied. Sigma naught has to be less than 2 sigma. Right. So if I have this neutral brane, neutral domain bar, and it has a coupling with this domain bar between the theta and ADS, then there will be this coupling, and now one can show that there is a solution which basically looks like this.
So this domain one is a static solution. Is it a solid one? I mean, it has a finite energy configuration.
So this is a so what is it? If you go to 4 dimension, then this is a spherical symmetric brane, this spherical symmetric dimension bond object has a finite tension, a fixed finite tension. When I reduce it to the 2-dimensional set of it, it's just a particle. I mean, you can think in the case of, in this case, this domain bar is just a domain bar corresponding to the phi configuration that separates the two backgrounds, except that now they are assuming that the thickness is thin enough that I can approximate it by just effectively as a domain bar. Don't focus inside the details of that.
Is your understanding of this domain wall from the boundary perspective, like from the Schwarzian or the Swag? What does this domain wall? What does this particle correspond to?
No, I don't have an understanding of what it's about. So, if you talk about the one-sided case in which you identify the two sides, and in that case, I think this corresponds to inserting some particular projection in SYK and then doing the Euclidean evolution. So that is, I think that is the solutions that maybe first was conceived by Corcola and Madsen.
But does that description help you to answer this question, whether you have such a coupling between this, this uncharged brane and the the charged one that it would be?
Yeah, I don't know, because for them, so first of all, there is also this identification of the two sides. So it's not exactly what I'm talking about. Secondly, I'm not sure about this particular landscape with the Sitter vacuum. I don't know if such a thing exists in SYK, whatever is the dual to SYK. Right? You need this domain corresponds to this particular heat configuration that interpolates between the Sitter and the Minkowski vacuum. But of course, this is
this everything you're talking about is within this two-dimensional context. One could imagine that this process can be mimicked also in the one-dimensional SYK.
Yeah, I mean that is actually some maybe one of the third motivation that I didn't mention here. But yeah, that is indeed one of the motivations that once in this setup I have really embedded the Sitter inside ADS, the Sitter 2 inside ADS2, and now there is a hope that they can probably study the Sitter 2 using if you have a dual to ADS2, you can study it there. But no, at least so far I don't have a detailed understanding of, not even rough understanding of this from a boundary perspective. Okay, so now let me just the only thing I here I can say is to maybe I can a little bit motivate this part of kind of coupling that I consider here to just say that it's not totally unimaginable to have this kind of coupling. So let us just consider a two-dimensional system.
Sorry to interrupt again. So if I were to know precisely the whole property of SYK, which includes not just Schwarzschild but all these particles, I would have to know this particular kind of coupling, right?
You said in that case you would know this.
I would know this. I would know about this coupling. I would know about these particles that correspond to your domain walls, and I would know about this coupling. So we will compute out the probabilities of all.
Right. In principle, you would know whether there is actually this vacuum or not.
Yes.
So if this vacuum exists, you know that there is a particle that corresponds to the domain wall between the two. Yes. Should I go to this board or is it?
No.
So now let us just consider a two-dimensional model, and I want to motivate this coupling between this neutral brane and the domain was between the sitter and ADS. So here we can think about a king anti-king configuration. So the king anti-king. Okay, so this is, I guess, self-explanatory. So this is phi, this is x, this is the potential V of phi. So consider a configuration that is in this vacuum, and then it goes to the other vacuum and comes back. So this is the king, and this is the anti-king. And here we know that there is also fundamental excitation at the bottom of this potential. And there is a coupling between the fundamental particle at the bottom of this potential and king anti-king. So there will be a cubic coupling phi kk bar. However, the process phi decaying to king anti-king will be forbidden kinematically if we are at big coupling, because king anti-king configuration is very heavy compared to the fundamental particle. So this is this will be a forbidden process in Lorentzian signature. However, that exactly means that in Euclidean signature that would be an allowed process, because here think of this sigma as mass of the king or anti-king, and sigma naught as mass of the fundamental particle. So if the fundamental particle is lighter than the king and anti-king, there will be this Euclidean vertex which is allowed. Now the whole question is that whether we can put this Euclidean vertex which is allowed inside some general geometry so that we can rotate it into Lorentzian. But this is a little bit similar to here. For instance, if we imagine having also an axion coupled to our charged particle, but axion was much lighter than the charged particle. Then we could imagine having considering the decay of the axion into those charged particles. Then if the axion is lighter than those, if we put it in a background field. So this is one way to think about this process that is happening here. There is a light excitation here that will decay into heavier domain walls between the between ADS and the sitter. But because, so normally it wouldn't happen, but once we consider the gravitational field, then it will be allowed. So the full solution that we construct, it will look like this. Is this still replaceable? So there are the asymptotic regions. Then there is this. Charged brane. It decays into the domain walls, and then there will The domain was go and bounce back and then go back. So now I can draw it like this way. It's always challenging to draw. So you should think of these two points as being identified. And this, so here is the theta region, this is the ABS region. Of course, all of them Euclidean. However, this solution that it has the moment of reflection symmetry. That is the point that if we cut the solution and big rotated into Lorentzian, then it will arrive here. Okay, so I guess I should stop. I said most of the things that I wanted to say. This geometry, this solution that I'm finding here, it has an Euclidean action, which is maybe I go here. Let me go here. Is it okay?
Yeah.
So let's just say a couple of words about probability. For probability, we want to compute the Euclidean action or changing the Euclidean action. For that particular solution, it is computable, but just from the parametrics of the setup, one can expect how it is going to work. It will be a order of phi. Phi, remember, is basically what is controlling the near extremality of my solution. The phi is a small number. It is something of order of phi times the quantity that one naturally exists, basic mini RE squared. The extremal radius is the square divided by G nu. In particular, this is much less than the Bekenstein-Hawking outro, which means that the probability, so probability we expect it to be e to the minus 2 delta S Euclidean. This is of course small, but it's not too suppressed. It is much bigger than 1 over the number of matrices of the black. Okay, I guess I stop here for questions. But essentially, the message is that this seems to give. So there are many weird ingredients in this setup, but they are ingredients that one can imagine in a QFT. They could be field theory models in which these ingredients exist. So none of them seem to be particularly forbidden. And as a result, it seems to suggest that this uptunneling to the city is not a forbidden process.
After you rotate it back to around some time, so what happens in the future solution?
What happens in the future?
Right.
So after I rotate it back, it is this bubble of the theta, which is separated from asymptotic observers by horizons and singularity. So it is causally disconnected from asymptotic Minkowski observers. But inside here, you will have inflation. If you go sufficiently far to the future here, it will be just normal inflation.
But also then these black holes eventually evaporate.
And you separate from this inflating bubble will separate from the.
So is it possible?
Because what happens they will block the same operation charge Q.
Well, but then they will still evaporate. Or I shouldn't be fair for them. Eventually will. No, but
Monopause.
right. Yeah, the mono. No, but basically what I'm trying to ask is, can you think feels like from the point of view because we started with setup and you have like stable Minkowski vacuum. So presumably we usually think, okay, in this situation like that, everything can be described by S matrix. Like that vacuum. So what in terms of that S matrix, what does it know about this universe being created there? Because somehow this bubble looks like it separates completely from the final state, right? So,
So that's matrix in this geometry.
well, I'm trying to think about gravitational symmetrics and all this. Yeah.
I mean, I guess it knows about what happens here in the same way that it knows about what happens to observers who jump inside the black hole and burn.
But here, in principle, you may have inside the, like in this inflationary universe, you can may have huge entropy, right?
That's right. That's right.
Which is much larger than entropy of the horizon.
Yeah, that's very true. That is actually something that might seem confusing.
So that's just that from outside you won't actually know much about it because your entanglement between outside observer and inside is limited by Wittgenstein entropy of the horizon, right?
Right.
And so somehow it looks like much of this life in this interior universe is somehow completely
Right. Then, I mean, you could also, I mean, there are these questions. You could also ask this question. Maybe it's not as sharp as here. The nice thing about it is that you can relatively sharply formulate. But even just having the theta universe by itself, you can ask: is there an interpretation of the Gibbons-Hawking entropy of the theta as we compare it from this observers who live in the inflationary universe and they have big universe and can probably have much more entropy than that. I think there are some claims that it should be bounded by that, but it sounds a little bit. Okay, so one thing that I can say is that perhaps there is a finite number of states that I can have for this universe, and that because this might be a state of a very large number of degrees of freedom, but the number of the states of that large number of possibilities that I have for those many large number of degrees of freedom is finite. Like having an unstable particle that decays into many degrees of freedom, but that unstable particle might have a finite dimension here.
Is there a way, for example, to question if we were talking data similar to what Schenker does in that expression in reality? And basically we'll do the question data and then we do like gas transformation to get the density of states for that metric configuration. And we know, for example, if the density of states is continuum, then you have infinite entropy, but if the density of states might be discrete, then we do have a finite amount of degrees of freedom for this configuration. Similar thinking on the theory in the boundary. I mean, because I mean, if I have finite states, maybe to try to calculate the density of states that represents the dual of this two-dimensional the theta inside the theta. Can we do that? Calculate the density of states similar to what Schenker does in pure Schenker gravity.
Yeah, in principle, it is. I mean, I guess I cannot do it as precisely as they do because there is a lot of simplification in that pure JT.
They have a much easier configuration for the metric.
Right. So here, I guess you can find the exponent, the semi-classic, but the action, saddle point contribution to the partition function, and then ask what it predicts. Yeah, I haven't done that.
Because I mean, I understood, so I know the bit, but always my disappointing point was that we always get the density of states and it's always continuum. So in the end sense that we are not solving information kind of equation balance because we have we don't have a discrete row that would tell us at the end of this funnel. So maybe here, I don't know, maybe we get some density of space that represents this immersion space. I don't know.
Can you comment a little bit on the relationship? There's
Oh.
two different proposals for.
Sure, yes. So their setup is relatively simpler compared to mine, or at least they include less ingredients than what I. Basically, they consider the following tunneling process. These two approximations are also made then. But they basically consider tunneling between these two geometries. One of them, they call it buildable bubble. And the other one is the one that contains inflation.
So do they deal directly with the four-dimensional geometry and find the some solution like the tunnels between these two geometries?
Right, that's right. Yes. Although it's still, I mean, these two assumptions basically reduce the problem to solving for a single degree of freedom, which is just the motion of the domain. Also, in my case, I would basically deal with the motion of domain walls and the decay interaction between the domain walls, because by Birkhoff theorem, the geometries will be fixed.
But in their description, if you try to follow what you just said, if in their competition reduce it to two-dimensional, can that problem be again kind of rephrased in terms of the SY state?
I don't think so, because it's not because the size of this field, it's not really, even if it, I mean, it is, again, you have a size of this 2 and the TR part of the metric, that is still the case, but the size of this 2 is changing by much through this solution. It's not that I'm focusing on a region when the size of this, it's not an approximately two-dimensional setup. But well, I mean, okay, so anyway, these are the details. The point is that basically they consider the situation when the setup when I have a small bubble. So this is imagine this is a bubble that could be made even in field theory, a bubble that decays, doesn't inflate. That is a law, doesn't seem to be any problem with that. So they ask, is there an instant on a Euclidean solution that interpolates between this symmetric cut of this geometry to the symmetric cut of that? So that's essentially the question that they ask. The geometry that they find for this is singular in the sense that actually I don't fully understand the singularities. I think basically the way it works is that you have it's not really a manifold, the solution that they found, because you have to cover part of the manifold, you have to cover it twice.
I see. So it's an orbital type singularity, not something worse.
Looks like this, but I'm not sure actually. Looks like the kind of singularity that they have is of this, because so this also you have Schwarzschild, which we call the cigar geometry. But then you want to connect it to this de Sitter bubble, and I think the way that you can connect it to the de Sitter bubble, satisfying the condition that this domain wall has a positive tension, is that you actually glue together two of these cigar geometries and then put the de Sitter bubble here. So this is the singular point, right? I mean, it doesn't look exactly like an orbital singularity.
No, it's not. And what's the probability that they find the comparable?
Okay, so they despite the singularity, I think they have a way of getting a finite probability. The answer that they are getting is slightly confusing. It's not very counterintuitive to me, because, for instance, in their solution, you can send the mass of the black hole to 0, and still you will have a finite probability. So that you can basically decouple the size of the ds from the size of the black hole. But for instance, in my setup, the size of the density and the size of black hole are connected to each other. They are more or less of the same size. Yeah, this is one confusing aspect. You basically can send the Schwarzschild mass to 0 and stay with the finite probability for this tunnel. In fact, recently, some people, including Fernando Quevedo, was using this fact to argue that you will have some finite probability for nucleating closed universes. But again, there is no consensus about the validity of this solution because of this singularity.
The obvious question would be, if you allow this kind of singularity, then where do you stop?
Right. Yeah. There are some comments. There was a paper by Maros and Fu about similar questions. They were perhaps more interested in bags of gold geometry, but there they study also this embedding of the theta into asymptotic anti-theta universe. And they work with similar setups, and they have some kind of no-go theory modulo this kind of singularities. And then they comment on why they think this is not a lot thing in the. We shouldn't allow this singularity. But to be honest, I don't have a strong opinion either way.
Yeah, the next semester.
Yeah, it was interesting. The audio and the
Camera?
Right, the